This is week 10 of the applied thermodynamics course, and this week we will be looking at vapor compression cycles, and also vapor absorption cycle. These are both are refrigeration cycles. So till the previous week, what we saw was power producing cycles. So or you can say heat engines. So we used the basis the Carnot cycle as the reference, which gives you maximum efficiency. In case of a refrigeration cycle, it's the other way around. It's a reverse Carnot cycle. So that is our reference here, and we'll see how vapor compression refrigeration system works, VCRS in short. So how that works, and also in vapor absorption refrigeration system, VARS. So to give you a recap, so till previous week we saw initially started with the Carnot cycle, which is also a heat engine. We saw it as a heat engine. Then Rankine cycle and Brayton cycle, and a cycle diesel and Otto, which is in internal combustion engines. Then also the Brayton cycle in a gas turbine power plant, and also in aircraft, how it will work. So this is all we saw. In each of the case, it was we are getting some work out of it, and we are giving some input. That input was in form of heat, or heat generated because of the combustion. In vapor compression or this refrigeration cycle, so this also you see it across many parts. So let it be at home, your air conditioners and your refrigerator both runs in your VCRS, and then maybe in malls you have bigger chillers and or deep freezers, so on. So the applications are many, making with various temperature ranges, taking from your AC, which is max 18 to 26 we are running, and your refrigerator, your it goes to minus 10 and so on, and you have deep freezers minus 30, and in case of pharmaceuticals and biomedical applications you go to minus 80, and much more applications for this cycles. So with that note, we'll see how an VCRS system works. So if you see in a glance, this looks similar to what we saw in the previous weeks. This has a compressor, this has a condenser and evaporator. So if you see, even in a Brayton cycle, you had a compressor, you had a heating addition part, and then it was a expansion, and then also again the heat exchanger. So that was the 4 components. So here also we have one compressing component, one expansion component, and 2 heat exchangers. So initially what happens is, start at state 1, you are compressing it through the compressor, and the compressor takes some work to compress the fluid from state 1 to 4, and then it's passed to a condenser. So condenser, what happens is, the fluid coming out of the compressor is at a higher pressure and temperature, so cooling it and condensing it to a liquid state. So, and in some cases subcooled liquid, and then that is expanded through an expansion valve, and then from expansion valve you are sending it to an evaporator. So this fluid here at state 9 is at lower pressure, and the temperature is also lower, and then this is picks up heat, and in terms cools your space what is required, and then it comes out of state 1. So that one ideally is we require it to be at a saturated vapor, or to avoid any liquid entering compressor, since liquids are incompressible, so that may damage your compressor. so you don't want any liquid to be going inside a compressor. So this same discussion we also saw when we were discussing an Carnot cycle and why it cannot be used in a two-phase region, and we moved it to a Rankine cycle. So similarly, we don't want any two-phase to have in the compressor. So we generally keep a additional some heat to have a superheated state in the compressor inlet. And if you see here, expansion valve. So this expansion valve is operating on the principles of Joule-Thomson's effect. So this is also an expansion process. So in previous case, we had turbines. We were doing the expansion. So even turbines will give you a temperature drop with reduction in pressure, but changing it with the valve. So this you are moving away. You don't want any moving component now. So that is one advantage. In case of valve, there is no moving part. So there is an additional increased reliability of the system. So in that point of view, going with valve is an advantage. Another advantage is you are operating here in a two-phase region, so you don't want that. So your inlet will be in a liquid state, and then your exit is in a two-phase state. It's a liquid plus vapor. And in the Joule-Thomson's effect, you are when your inlet temperature is less than the inversion temperature, so there will always be a temperature drop in pressure. But if you lie outside the temperature inversion temperatures, you will have an increase in temperature. So generally the normal fluids which we see, all inversion temperatures are lower, so we always see a reduction in temperature with respect to pressure, except if you name a fluid where you will have a increase in temperature with pressure. The decrease in pressure is hydrogen and helium. So the other general fluids will always give you a drop. So this is the schematic of the cycle, and if you see, the process is shown in a TS diagram. So 1 to 2 is your compression process. So 1 to 2, you are giving some work and you are compressing the fluid. So ideally this is an irreversible adiabatic process, so your entropy will remain constant, and then you are after reaching state 2, so state 2 is at higher temperature, and you use the ambient to cool the fluid to state 3. So 3, and then you expand it across the expansion valve. So this process, your enthalpy will be constant. So if you apply a steady flow energy equation across the expansion valve, so there is no heat addition and there is no work addition. So Q minus W is 0, and then whatever energy is coming in is going out. So if you neglect the kinetic energy and potential energy, your enthalpy will remain same. So across the valve, your enthalpy remains same. So 3 to 4, then 4 to 1 is your evaporator, where you are getting the required cooling. So this is an vapor compression refrigerant system. So what happens in a vapor absorption refrigeration system? So in vapor absorption refrigeration system, you are taking away compressor and you are putting this thermal compressor. So what is this? So it's like a refrigerator or a heat pump run with the heat engine. So that's a schematic equivalent of an vapor absorption refrigerant system. So why to do so? So in compressor, if you see, you're compressing air, so a fluid which is at a vapor state. So we know compressor work is minus V dP. Yeah. So your specific volume of your vapor state will be larger compared to a liquid state. So to reduce the work given, you can use a pump. So that's one, and the vapor absorption is to generate this thermal compressor. So this is generally used when you have excess of heat which is available with you. Uh, for example, you are in a plant and you in the process streams, you have additional stream which is at higher excess heat which is dumped, so you can basically make use of those. So in that case you can use that heat to run in vapor absorption refrigerant system, so where you have a cooling requirement, so you can use the waste heat in utilizing vapor absorption refrigerant system, and that heat is given in a generator. So in this vapor absorption system, you have two in the fluid you have two parts. One is an absorbent and your refrigerant. So these two are forms a mixture. So and that rotates in this thermal compressor, and in the outer loop with the condenser, expansion valve and the evaporator, you have the refrigerant flowing. So what happens is, initially you have a mixture of the absorber and the refrigerant, which you for in this case you can say ammonia and water. So you have ammonia and water that mixture in the absorber, which is pumped through the pump to the generator. So absorber will reject heat, because whatever from the evaporator you will have ammonia. So ammonia will mix with water, so that water will contain lower amount of ammonia which is coming through the valve. So when this mixture, will be a heat rejection. So in the absorber there is heat rejection, and this mixture is pumped through the pump to the generator. So in the generator you make use of that excess heat which is available, and you boil off the ammonia, and that ammonia goes through the condenser, and that water so now is a concentrated in terms of water. The concentrated fluid in terms of water is then passed through a valve and sent to an absorber. So you have only ammonia which is coming out to the condenser, and then this is again the same as the vapor compression cycle. So only thing is, the compressor is now replaced with a thermal compressor, which is pumped via the mixture the water and the ammonia. So the other mixture combination is your lithium bromide and water. In this case, water will be your refrigerant. So that is an vapor absorption refrigerant system. So with that, we'll see some of MCQs and problem. The first one is in a vapor compression refrigeration system, which component experiences the lowest temperature? A. Condenser, B. Evaporator, C. Compressor, and D. Expansion valve. So if you see in the compressor, inlet is at saturated vapor at low temperature, then you are compressing it to a higher pressure and temperature. In condenser, you are then condensing back, and you cannot go below your ambient temperature. case of ideal assumption that which you have in a Carnot cycle, so the delta T being 0. So in that case, at max you can go with that assumption, you can go to the ambient temperature, and then the expansion valve, you will have that input and it will produce a lower temperature, and you have the evaporator. So if you see, the evaporator is the one which is having the lowest temperature across the whole component. So answer is B, evaporator. Next one is centrifugal compressors are preferred for low evaporator pressure and refrigerants with large specific volumes at lower pressure. So answer is true. So centrifugal compressors are preferred for lower evaporator pressures and which has a large specific volume. So next is, in a refrigeration system, the expansion device is connected between the dash A, compressor and condenser, B, compressor and evaporator, C, condenser and evaporator, D, none of the above. So if we see the cycle, first you have compressor, then you have condenser, then you are having expansion valve, and then the evaporator. So it is connected between the condenser and evaporator. So answer is option C, condenser and evaporator. The next is, in a vapor absorption refrigeration system, the compressor of the vapor compression system is replaced by dash A, liquid pump, B, generator, C, absorber, D, absorber, generator and a liquid pump. So this is just the comparison which we saw between the VCRS and the VRS system. So the pump compressor is replaced by an absorber, generator and liquid pump as well as a valve. So answer is option D. So moving on, the next is, gas refrigeration cycle works on the principle of dash A, Carnot cycle, B, Atkinson cycle, C, Joule cycle, D, Rankine cycle. So answer is C, Joule cycle. So Joule cycle, you see it's an reversed Brayton cycle. So next is, absorption refrigeration system normally uses the refrigerant dash A, CO2, B, R12, C, R134A, D, ammonia. So it's examples which we saw in the vapor absorption refrigerant system. So answer is D, ammonia. Though now people are using R134A, so but the traditional most preferred one is the ammonia in absorption refrigerant system. Also this is a natural fluid, and now all the countries and are trying to move towards natural refrigerants. So answer is option D, ammonia. The next question is, a refrigeration system operates on a reversed Carnot cycle. The temperature in the condenser coil is 27 degrees Celsius, and that in the evaporator coil is minus 23 degrees Celsius. For a work input of 1 kilowatt, the heat received from the low temperature reservoir is, so Carnot cycle, normally the efficiency in a Carnot cycle is defined as your heat as a work done for the input heat which is given, so that is the desired output divided by the input given. So in this case, your output desired output is your heat, how much heat you are taking away, so in the evaporator, so that is your desired output, and the input is your work which is given to drive the compressor. So here it's given one work input is 1 kilowatt, so this Q by W is termed as COP, a coefficient of performance, and this will always be greater than 1 for a heat pump. And so heat pump is nothing but that your desired output is your condenser heat which is rejected, so that divided by the work. So in a refrigerator it is the evaporator, and in the heat pump it's the condenser heat. So for in terms of COP, the COP of heat pump will be always be greater than 1. So if you do an energy balance, you see that you are you have to dump the work which you are giving in the compressor, and the heat which you are picking up in the evaporator, both has to be rejected in the condenser. So the COP will always be greater than the work which is the heat which you are rejecting in to the ambient in the condenser is always greater than W. So COP is always greater than 1 in case of an heat pump. So with that note, COP for this reverse Carnot cycle is operating as a refrigeration system. So here it is Q evaporator divided by work done. So work done is 1. So this is equal to COP. So Q by Q condenser minus Q evaporator. So this will be equal to your evaporator temperature divided by condenser temperature minus evaporator temperature. So that is your COP. So evaporator temperature is minus 23 and condenser temperature is 27. So evaporator temperature in terms of Kelvin is 273 minus 23, which will come out to be 250 Kelvin. So Q1 by W equals the evaporator temperature divided by condenser temperature minus evaporator temperature. So substituting the values, you will find out Q as 5 kilowatts. So for 1 kilowatt of heat work which you are giving, you are taking away 5 kilowatts, you are getting cooling of 5 kilowatts. The next question is, we have a cold storage which is to be maintained at minus 5 degrees Celsius while the surroundings are at 35 degrees Celsius. The heat leakage from the surrounding into the cold storage is estimated to be 29 kilowatt. So what is given is, we have a cold storage, so it's basically a room where it's a refrigerated space. So there the temperature is minus 5 degrees Celsius, so that is your evaporator temperature, and then the surrounding is at 35 degrees Celsius, and they are saying the heat which is coming in is estimated as 29 kilowatts. So the actual COP of the refrigerant plant is 1/3 of an ideal plant working between the same temperature. So the power required to drive the plant is dash. So an ideal refrigeration system works in the principle of reverse Carnot cycle, so that will give you the ideal COP. So this will be working between minus 5 and 35 degrees Celsius, which is the ambient temperature and the evaporator temperature which you need, and that will give you the ideal COP. but the actual refrigerant system COP is 1/3 of this. So it will take thrice the amount of work for the same amount of cooling to be provided as the ideal refrigerant system. So suppose for you are getting W amount for 1 kilowatt of cooling in an ideal refrigeration Carnot system, then this actual refrigeration system will take 3 kilowatts for the same amount of cooling to be provided. So here the evaporator temperature is given, and the condensing temperature is also given, and the Q heat. So for the cold storage, if it's at -5 degrees Celsius, for it to remain at -5 degrees Celsius, so the cooling has to be provided such that whatever heat is coming in will be taken away, so that it will remain at the same state of -5 degrees Celsius. So the cooling capacity required is equal to the heat in leak. So you know Q, so you have to just estimate W. So cold storage temperature, so evaporator temperature is -5, which is equal to, converting it to Kelvin, it is 268 Kelvin, and in surrounding temperature, this is the ambient temperature or the condensing temperature in this case, is 35 degrees Celsius. So converting that into Kelvin, it will give you 308 Kelvin. So heat leakage from the surrounding is 29 kilowatt. So the actual COP is 1/3 of the ideal COP. So calculating the ideal COP, which is evaporator temperature divided by the temperature lift, or can say the condenser temperature minus the evaporator temperature, gives you 268 by 40, which is 6.7. So the ideal COP is 6.7. So actual COP is 1/3 of this ideal COP. So 1/3 into 6.7, which gives you 2.233. So that is the actual COP. So we know the heat inlet or the cooling capacity which has to be provided. Q is 29 kilowatt. So with that and the COP is nothing but your desired output by the input. So desired output is my cooling load or the heat which has to be removed, divided by the work which we have to provide. So with that we can estimate W. The actual COP is 2.233 and the cooling capacity is 229. So with that, W will be 29 divided by 2.233 and it will come out to be close to 13 kilowatts. So the answer is option B, 13 kilowatts. So the next question is on a vapor absorption refrigerant system. So the operating temperature of a single stage vapor absorption refrigeration system for different components are as follows. The generator is at 80 degrees Celsius, the condenser and absorber are at 35 degrees Celsius, the evaporator is at 0 degrees Celsius. If the pump work is negligible, then the ideal COP of the system is dash. So as I previously told while discussing on vapor absorption system, how that is equivalent to a heat engine driving a refrigerator. So we'll use that concept here. So if you see, the COP of the vapor absorption refrigerant system is equivalent to the efficiency of the heat engine, that is the heat engine operating between the generator and the absorber. So you have two systems. If you take into account, I will go back to the diagram so it will be easier to understand. So we see this comprises of two parts. So one is which the refrigerant is running, and the mixture part. So this blue region, which is a thermal compressor, it's equivalent to a heat engine, which is applying heat and producing work. So this pump work is negligible. So this heat engine is operated between the generator and the absorber. So the absorber and condenser temperature are both same. So the heat engine is operated between generator and absorber. So this in terms is driving the refrigerator. So the refrigerator is operated between the condenser and the evaporator temperature. So the COP of the vapor absorption refrigeration system is equal to the COP of the refrigerator is operating between the condenser and the evaporator multiplied by the efficiency of the heat engine. So here heat engine is operated between the generator and the absorber. So if you see COP is Q by W, and this W is generated by this engine, so is equal to W by the Q which you are providing, Q in. So with that, the COP of the VRS system will look like this. So T1 minus Tc by Tg is the efficiency of the heat engine into TE by Tc minus Te is the COP of the refrigerator. So Tg is your generator temperature, and Tc is your absorber or the condenser temperature, both are same, and Te is evaporator temperature. So converting those into Kelvin and substituting, so generator temperature is 353 Kelvin, condenser temperature is 308 Kelvin, evaporator temperature is 273 Kelvin. So substituting this expression, you will get COP as 0.994. So if you see, this is the COP of a vapor absorption refrigerant system, and you can see that this is lower compared to the COP of a vapor compression refrigerant system. Okay. Next is, during the throttling expansion process in the vapor compression refrigerant system, specific volume remains same. So the answer is false, because it's again being an expansion process, your volume increases. So expansion is basically your volume is increasing. That's what you call is an expansion. So this is also an expansion process. So your specific volume will not remain same. So answer is false. So with that, we have finished the MCQs. Now we'll move into the numericals. The first one is a reversed Carnot cycle air conditioner of 1 ton refrigeration. A reverse Carnot cycle air conditioner of 1 ton refrigeration capacity operates with cooling coil temperature to 5 degrees Celsius. So the cooling coil temperature is your evaporator temperature, that's required at 5 degrees Celsius. The surrounding air at 43 degrees Celsius is used as a cooling medium, rising to a temperature of 53 degrees Celsius. The temperature of heat rejection is 55 degrees Celsius. The overall heat transfer coefficient of the heat exchanger between the working substance and the surrounding air is 250 watt per meter square Kelvin. Determine the mass flow rate of the surrounding air entering the heat exchanger area of the heat exchanger, COP and power consumption of the air conditioner. So that's the first part of the question. The second part is, if water at 30 degrees Celsius is used as a cooling medium in the same heat exchanger, will its area be adequate or inadequate for necessary heat rejection? Assume that the mass flow rate of water remains the same as that of air. Also for water, U is 2500 watt per meter square Kelvin. So that is the second part of the question. The third part is, if the area is reduced to 1 meter square, what will be the temperature of heat rejection, temperature rise of water, COP, power consumption, percentage saving in power consumption, and percentage reduction in the heat exchange area as compared with air as cooling medium? So that is the third part of the question. So we'll go one by one. We'll start the first one. So we are taking into account the condensate. So your temperature of heat rejection is 55 degrees Celsius, and the air is used as a cooling medium, and there the air is coming in at 43 degrees Celsius and going out at 53 degrees Celsius. So that is known. With that, and also the evaporator temperature is given at 5 degrees Celsius. So basically your condensate temperature is 55 degrees Celsius. So that is your condensate temperature, and your evaporator temperature is 5 degrees Celsius. So with both of this temperature, we can estimate the COP. So COP is nothing but your evaporator temperature. Q by W is your evaporator temperature divided by condenser minus evaporator temperature. So your evaporator temperature is 5 degrees. So converting that into Kelvin will be 278 divided by your temperature difference between the condenser and the evaporator, which is 50. So that will give you a COP of 5.56. Then with this we can estimate the power consumption. So power consumption is, your COP is Q by W, so W is Q by COP. So Q is given as 1 ton of refrigeration, which is equal to 3.5167. So or you can take 3.52. So actually 3.5167 divided by 5.56, which gives you 0.63 kilowatt. So that is the work requirement. For this, the heat rejected, because we need to know how much heat is getting rejected in the condenser. So we know the inlet and outlet temperature of the air which is coming in. To estimate the mass flow rate and area, we also need the amount of heat is getting rejected. So that we can find out. We know the heat added to the vapor compression system, the evaporator, plus the work done is what is getting rejected in the condenser. So the condenser heat rejection is equals to 3.5167, which is the cooling capacity, plus the work which is inputted to the system, which is 0.63, which will give you 4.15 kilowatt. So this is the total amount of heat which is getting rejected in the condenser. Now to estimate the mass flow rate, you can find out Q is mCp delta T. So assuming air is ideal gas and it doesn't Cp doesn't vary with pressure and temperature, so mass will be Q by Cp delta T, and Q is 4.15 in this case, and Cp is 1.005 for air, 0.05 kilojoule per kg Kelvin, and so Q is also in kilowatt and Cp is also in kilojoules, and into delta T we see a change in the air temperature, which is all given. The inlet is at 43 and the outlet is 53, so there is a 10 degrees rise in temperature. So 4.15 divided by 1.005 into 10 will give you 0.413 kg per second. So that is the mass of cooling air which is passed through the condenser. Next is, I need to find out the area. So I know the overall heat transfer coefficient U. So Q in terms of the heat transfer coefficient will be UA delta T, or the LMTD, logarithmic mean temperature difference. So for that I need to find out the logarithmic mean temperature difference. Assuming condenser temperature is same, so that is a constant temperature 55, and your inlet is at 43 and outlet is 53. So with this we can find out LMTD, which is the temperature difference across the either ends. So 55 minus 43 and 55 minus 53. So that are the two delta T's, delta T1 and delta T2. So delta Tm, which is LMTD, is delta T1 minus delta T2 divided by ln delta T1 by delta T2. So substituting these values will give me 5.58 degrees Celsius. So that is logarithmic mean temperature difference. So for this temperature difference I can find out area, which is Q by U into logarithmic mean temperature difference. So substituting the values, so Q is 4.15 kilowatts, so 4.15 into 10 power 3 divided by U is 250 watt per meter square Kelvin into your temperature difference 5.58, which gives me area as 2.975 meter square. So with this I finished the first part of the question with air. So I know all the properties, the parameters with when it is operating with air. So now we'll move on to water as the cooling medium. So in this case the condensing temperature, since your compressor, your water is at 30 degrees Celsius, we'll assume the first that your condensing temperature is 35 degrees Celsius. So with that the CUP comes out to be 9.27 for same 5 degrees evaporator temperature, and the Q, which is has to be rejected, will come out to be 3.9 kilowatt for this case. So delta T across the hot end will come out to be Q at the condenser divided by Cp. Again Cp is 4.186 for water, and we are using the same mass flow rate as in air, which we found out 0.413. So this gives me 2.26 degrees Celsius rise in temperature. So the water is coming in as 30 and going out at 32.26 degrees Celsius. So this, the logarithmic mean temperature difference is 3.76 degrees Celsius for 35 degrees condensing temperature. So with that the area comes out to be 0.41 meter square. So we find the actual area is 2.975 meter square. It is seen that, so since the area with this conditions, the area is smaller, so with the actual area is higher compared to this area. So the condensing temperature will be even lesser than 35 degrees Celsius. So second approximate temperature is, we will assume it to be 33 degrees Celsius. So with that area, which will come again going through the same process, the area will come out to be 0.95 meter square. So if you see, the area is still lower, and it's close to 1/4 of the actual area. So it will be, the condensing temperature will be even lower. So even if you take your temperature to be 32.24, so that mean temperature difference is 1.12, the area requirement comes out to be 1.38 meter square, which is still less than the actual area. So hence the area of the heat exchanger is more than what is required. So, and for this cooling requirement, the evaporator size could be reduced to 1/3 for it to be working. So that's what is been asked here. So assuming that the mass flow rate of water remains the same as of air, we need to find out whether the area is adequate or inadequate for the necessary heat rejection. So this is more than adequate. So and we require just the 1/3 of that area. Next is, if we are reducing this area to 1 meter square, then what is the process? So by iteration we find the solution again. So condensing temperature is 32.94 square degrees Celsius. So COP is 9.95 and Q is 3.87 kilowatt. So delta TH is your Q by MCP. So that will come out to be 2.24. With that again we can find out the exit temperature, and the mean temperature difference, logarithmic mean temperature, is 1.5, and with that it will come out to the area as 1 meter square. So with this, the power consumption is W, which is Q by the COP, which comes out to be 0.35 kilowatt. So saving in power is, previously with air it was running at 0.63, now it's giving 0.35. So the saving in power is 44%, and saving in area of heat exchanger is 66%. So that we'll move to the next question. A R134A vapor compression system operating at a condenser temperature of 40 degrees Celsius and an evaporator temperature of 0 degrees Celsius develops 15 tons of refrigeration. Using the pH diagram for R134A, determine A, the discharge temperature and mass flow rate of the refrigerant circulator, B, the theoretical piston displacement of the compressor and piston displacement per ton of refrigeration, C, the theoretical horsepower of the compressor and horsepower per ton of refrigeration, D, the heat rejected in the condenser, and E, the Carnot COP, the actual COP of the cycle. So this is what is given. So I'll break it into parts for it to be easier to understand. So you have a vapor compression system which is operating with R134A. The condenser temperature is given and evaporator temperature is given, 40 degrees Celsius and 0 degrees Celsius, and the cooling load or the cooling capacity of this is given as 15 tons of refrigeration. So 15 into 3.52 or 5167, and using the pH chart. So we will be using the pH chart for R134A. So the discharge temperature and mass flow rate of the refrigerant circulated, the theoretical piston displacement of the compressor, and so we need to find out the discharge temperature, mass flow rate of the refrigerant. So that is part A. Then we have to find out the theoretical piston displacement and the piston displacement per ton of refrigeration. Then we need to also find out the work done or the power requirement, and also heat rejection and the COP. So we'll see how to solve this. So this you have to use a pH diagram. So with the pH chart for corresponding to 40 degrees and 0 degrees Celsius, the pressures will be 0.295258 megapascal or 2.95 bar is the evaporator pressure, and your condenser pressure is 1.0166 MPa or 10.17 bar. So this is your pressure fixed evaporator and condenser pressures. then we'll find out your inlet condition, which is the enthalpy, which is the saturated vapor to the compressor. So that H1 corresponding in the pH chart, where you take the same pressure of 2.95 bar and the saturated vapor in the dome, the corresponding enthalpy will be 398.6 kilojoule per kg, and the specific volume and entropy there is 0.06931 is your specific volume, and entropy is 1.7541. So these are the inlet properties, and then here the other properties are H4 is your inlet to the evaporator, so that will be equal to the saturated liquid enthalpy, because your enthalpy is constant across your valve. So across in the same condensing pressure, so if you take the saturated liquid, so if you that enthalpy, which will be equal to the evaporator inlet enthalpy, is 256.41 kilojoule per kg. And so here with that, if we assume that it's in first the compression is isentropic, so for that case your entropy will remain same. So your entropy is 1.7541, which is at the inlet, plus Cp into ln the change in enthalpy. So if you do an entropy balance, it will be the entropy in plus your entropy change because of the temperature change. So Cp ln T2 by 313. So this will give you T2 as 317.6 Kelvin or 44.4 degrees Celsius. So with that will give you the exit temperature, and similarly the exit temperature, with that you can find out the actual temperature of the compressor exit. So H2 is H2 dash plus your change in temperature, the heat added Cp delta T. So H2 dash is 419.43 kilojoule kg, and your Cp temperature rise is your actual temperature is 317.6 and your temperature is 313. So that is the rise in temperature, which is 4.4 into Cp is 1.145. So that will give you enthalpy as 424.5 kilojoule per kg. So that is your exit enthalpy of the compressor. So if you see the work done across the compressor is H2 minus H1, and that will come out to be 25.9 kilojoule per kg, and the heat rejected heat taken in the evaporator is H1 minus H4. H1 is your inlet to the compressor or the exit of the evaporator, and 4 is your inlet to the evaporator. So that enthalpy is we have already found out. So substituting that, we'll get heat or the cooling capacity, specific cooling capacity is 142.19 kilojoule per kg. So with that we can find out the mass flow rate. So we know the total cooling capacity which we required, which is 15 tons, and divide by Q naught. So it will be 15 into if you this is converted into kg per minute, so it's 3.1567 into 60, so that will come out to be 211. So that is tons per minute, divided by your specific cooling capacity is 142.19, so it will come out to be 22.26 kg per minute. Next is the piston displacement, theoretical piston displacement of the compressor. So V dat is m dot into specific volume. So assuming theoretical ideal, so So you assuming volumetric efficiency is 1. So whatever displacement volume is there, so that will be equal to the mass going in. So mass into your specific volume. So mass we have found out 22.26 into your specific volume is 0.06931. So it will come out to be 1.4543 meter cube per minute. So that is your theoretical displacement volume. And it also we need to find out displacement volume per ton of refrigeration. So this is required for 15 tons. So 1.543 divided by 15 will give you volumes per ton. So 0.1029 meter cube per minute. Then we also need to find out the work done, the total power. So that is nothing but we have already found out H2 minus H1, which is 25.9 into your mass flow rate divide by this is in kg per minute mass. So divide by 60 will give you 9.61 kilowatt, and the horsepower is asked. So converting that into horsepower, you have to divide it by 746. So that will give you 12.88 horsepower, and horsepower per ton of refrigeration is 0.86. So this all is asked in C part, and D is the heat rejected in the condenser. So heat rejected is your exit of the compressor and inlet to the valve. So that is equal to the inlet to the evaporator. So H3 is equal to H4. So H2 substituting this values here. So it will come out to be 62.36 kilowatt. And the COP is your cooling load divided by the work done. So your mass gets cancelled, so you will just substitute this specific quantities here. So your specific quantity is 142.19 divided by 25.9, which comes out to be 5.49. So that is your COP. So the next question is similar to R134A. So R134A enters the compressor of a vapor compression refrigerant system at 120 kilopascal as a saturated vapor and leaves at 900 kilopascal and 75 degrees Celsius. So the refrigerant leaves the condenser as a saturated liquid. The rate of cooling provided by the system is 18,000 BTU per hour. So determine the mass flow rate of R134A, the COP of the cycle. So determine the COP of the cycle if the expansion value is replaced by an isentropic turbine. So do you recommend such replacement for refrigerant system? Determine the COP if the evaporator pressure is 160 kilopascal and the other values remain the same. So determine the COP if the condenser pressure is 800 kilopascal and other values remain the same. So in this case, you have a cycle is operating at 120 kilopascal evaporator pressure and 900 kilopascal condenser pressure. So that's the first part, and the second part is if you are changing the expansion valve to an using an isentropic turbine. So that's one case, and seeing how that affects the cycle. And then we are changing the evaporator pressure from 120 kilopascal to 160 kilopascal. So what is the COP in that case? And we are changing the condenser pressure next and seeing what is the change because of that in the COP. So this is your cycle which is depicted so in a TS diagram. So 1, 2s, 3, 4 is your ideal cycle, and 1 to 2 is your actual process. So this is 900 kilopascal and 120 kilopascal, which is the first part of the question. So there your compressor inlet is at 120 kilopascal and X is at 1 saturated vapor, and the exit is given as 900 kilopascal and 75 degrees Celsius. So with that you can locate the stage 2. So H1, first one from the pH chart we can find out as to 236.97 kilojoule per kg, and similarly the state 2 will come out to be 310.51 kilojoule per kg. So we have to just locate this point for pressure and temperature in the pH chart, so we get the enthalpy. And similarly P3 will be your saturated liquid, which is at 900 kilopascal, and that will be equal to H4. So H3 is equal to H4 in the first case because you have an expansion valve there, and that enthalpy is 101.61 kilojoule per kg. So for this cycle, the work input and removal per unit mass of refrigerant is, so work done is, we know in inlet and outlet to the compressor, so it is H2 minus H1, so this is all in specific work. So work input per unit mass of refrigerant, so H2 minus H1 is 310.51, this is the output, minus input 236.97 will give you 73.54 kilojoule per kg. And similarly the heat removal or the cooling load in for this refrigerator is H1 minus H4, so 236.97 minus 101.61 will give you 135.4 kilojoule per kg. So now we are converting this to find out the mass of refrigerant flow. So mass of refrigerant is nothing but the cooling load divided by the specific cooling load. So it is given as 18,000 BTU per hour. So that is equivalent to 1 kilowatt is equivalent to 3412.14 BTU per hour. So dividing by that, and we know the cooling capacity per unit mass of refrigerant, it's 135.4. So that will give you 5.275 kilowatt. So that is your cooling capacity required. Divide by 135.4 give you 0.039 kg per second. So this is your mass flow rate, and with that we can find out the COP of refrigerator is Q by W. So 135.4 divided by 73.54 will give you 1.84. So that is your COP. This is the actual COP of the cycle. So next is we are replacing this expansion valve by an isentropic turbine. So what happens is, instead of 3-4, now it follows 3-4s. So this is the process now, 3 to 4s. So the entropy will be same, so we have to follow the constant entropy line, and the enthalpy at this point, so P3 initially is 900 kilopascal and X3 is 0, so that entropy is 0.3738 kilojoule per kg Kelvin. So this state 2, the turbine exit is at 120 kilopascal and the same entropy. So with this we can locate this point, and the enthalpy corresponding to this state is 92.98 kilojoule per kg. So with this, the turbine work output we are getting as 8.63 kilojoule per kg, and the net work for the cycle is, so you are giving some work to the compressor, and also because of the replacing valve with turbine you are getting some work output. So the net work is 73.54. so because there is no change here, only the state 4 is changed to 4s, so the compressor part remains same, so the work for the compressor also remains same, is 73.54, and that minus your work generated in the turbine, so that gives you 64.91 kilojoule per kg. So your net work is reduced because of changing from valve to turbine. Next is QL, it gives you H1 minus H4s. So the load is now 236.97 minus 92.98, it gives you 144 kilojoule per kg, so that is also as increased. So the COP is 144 kilojoule per kg divided by 64.91 kilojoule per kg will give you 2.21. So we see previously it was 1.84, but changing from valve to turbine it increased to 2.21. So if you see, the COP increases by 20.1% by replacing the expansion valve by a turbine. This replacement makes thermodynamic sense since it decreases the work requirement and thus increases COP. However, this is not practical for household refrigeration and most other refrigeration systems. So this is what I talked at the start, that uh, so it increases, one is increasing regularity, and we have to operate this in a two-phase region, so which is difficult. So this may make thermodynamic sense, but it's not practical. We cannot implement it in an actual system. So the next is, if the evaporator pressure is 160 kilopascal, then your COP now, so we have to estimate, instead of 120 kilopascal, this line 1 to 4 line moves up a little bit to 120 to 160 kilopascal, and then you have to estimate now new state points 1 and 4. So doing so, your H1 will be 241.12 and H4 will be 101.61. So with that, the COP will be again H1 minus H4 divided by H2 minus H1. So that's what we did. We found out separately QL and W. So we are straight away finding COP substitute. So substituting these new H1 and H4 values will come out to be 2.01. So here H4 will remain same because that is coming from H3. So that will remain same. So basically your cooling capacity will go down in this case. Then so increasing the evaporator pressure from 120 to 160 kilopascal is increase the COP from 1.84 to 2.01, which is an increase of 9.2%. The next is you are decreasing the condenser pressure to 800 kilopascal. So again in this case your H4 will change, the rest of will be same. So even H2 will remain same. No, H2, your pressure is your temperature is same, but your pressure is changing. So previously the compressor exit is at given as 900 kilopascal and 75 degrees Celsius. Now it's 800 kilopascal and 75 degrees Celsius. So with that we have to estimate H2 and H4, and substituting these new values here, the COP is 1.89. So decreasing the condenser pressure from 900 to 800 kilopascal. So it has decreased the condensing temperature from 35.5 to 31.3 degrees Celsius. So practically what happens is, if your ambient temperature is it will be around 30, so you are basically reducing this temperature difference. So you have to go with a bigger sized heat exchangers. So that is from the practical point of view. But this also will increase your COP. So it's increasing from 1.84 to 1.89, which is an increase of 2.7%. Any doubt in this question? So basically what we did in this problem is, so VCRS with the simple VCRS system, we just varied some of the properties and saw its effect on the cycle. So basically in the VCRS system you have to first estimate this 3 points. So fourth one will get to be straight away from the other. So we have to just estimate the enthalpy, and you have to just estimate the other properties later on. So starting we have to just find out the enthalpies at each of the state points. Once that is located, the problem becomes easy. So okay, if there is no other query, and we'll move on to the next question. So here again this is an vapor compression system. So here your refrigerant is ammonia. So an ammonia ice plant operates between a condenser temperature of 35 degrees Celsius and an evaporator temperature of minus 15 degrees Celsius. It produces 10 tons of ice per day from water at 30 degrees Celsius to ice at minus 5 degrees Celsius. So what it basically does is, you have an refrigerator. The condenser temperature is 35 degrees Celsius and your evaporator temperature is minus 15 degrees Celsius, and this is used to produce ice. So for that you are passing water at 30 degrees Celsius and you are getting ice at minus 5 degrees Celsius. So this is what is happening. You are cooling this water using an refrigerator, and you have to produce 10 tons of ice per day. So using only tables of properties for ammonia, determine the capacity of the refrigeration plant, the mass flow rate of refrigerant, the discharge temperature, the compressor cylinder diameter and stroke if its volumetric efficiency is 0.65, and your RPM is 1200 RPM, and the stroke to bore ratio is given as 1.2. Next is the horsepower of the compressor motor if the adiabatic efficiency of the compressor is 0.85 and mechanical efficiency is 0.95, and you have to find out the theoretical and actual COP. So with that, we'll see how to solve this. The first is, we have to find out the refrigeration capacity. So the refrigeration capacity is given by the heat which you are taking in the evaporator. So here so this is your pH chart for the ammonia. So so the refrigeration capacity will get it from the water. So you have 10 tons of ice has to be produced. So that is 10 into 1 ton is 1000 kgs. So 10 into 1000 per day. So divided by 24 hours. So that will give you in terms of your cooling capacity per hour into this is M. So into Cp delta T. So but the water is going from 30 degrees Celsius to minus 5, and we know the water gets converted into ice at 0 degrees Celsius. So we also need to account for the latent heat. So this is taken into 3 parts. So first is the Cp of water. So 4.186 into its temperature change from 30 to 0. So that is the sensible cooling of water plus the latent heat is 335 plus the Cp of ice is 1.94 into the latent the cooling there. So this is minus 5, 0 to 5. So this will be 5. So that will give you 195,960 kilojoule per hour, or dividing by 3600 will get you 54.43 kilowatts. So that is the refrigeration capacity which is required. So from the table of ammonia, so this is ammonia. So we know H1, assuming it has saturated vapor, is minus 15 degrees Celsius. So the corresponding enthalpy for that is 1443.9 kilojoule per kg, and the entropy there is 5.8223 kilojoule per kg. And H4 is your saturated liquid. H3 is equal to H3 and saturated liquid temperature at 35 degrees Celsius, because evaporator temperature and condensing temperature is given. So there the enthalpy corresponding to that is 366.1, and with this we can find out the cooling capacity per unit mass of refrigerant. So that will be H1 minus H4 will come out to be 1077.8 kilojoule per kg. With this we can find out the mass flow rate of the refrigerant required. It will come out to be 181.7 kg per hour. So next is we need to find out the discharge temperature. So this is by the table chart. So here it's given at 35, 50 and 100. So we need to do some interpolation there for entropy. So our requirement is that entropy of the inlet condition, which is 5.8223. So you have to interpolate between 50 Kelvin and 100 Kelvin superheat. So that is 85 and 135. So on interpolating we can find out state 2 in the enthalpy. That will come around with temperature of 112.1 degrees Celsius. So after interpolating we get temperature. So that temperature will be 27.1 degrees Celsius superheat. So 35 plus 27.1, sorry 85 plus 27.1. So that will come out to be 112.1 degrees Celsius. So that is the temperature of the exit of the compressor. So next is we need to find out the piston displacement. So that is nothing but your volume flow rate divided by the piston volume, displacement volume, which is equal to your volumetric efficiency. So we know the mass flow rate, so multiplying by specific volume will give me the volume flow rate. So mass flow rate is 181.7 kg per hour into your specific volume at state 1, which is 0.509. So state 1 is here in the diagram, the corresponding volume there, specific volume, divided by the volumetric efficiency, which is given as 0.65, and your piston displacement volume is pi by 4 d square L into N. So d square into your L is given, the stroke to bore ratio is given, so 1.2 times of diameter into 1200 rpm. So converting in terms of hour, it will be divided by into 60. So because your mass flow rate is in kg per hour, so you are converting rpm into hour. So therefore from this we can find out diameter as 0.128 meter. So length is 1.2 times of this, so length is 0.154 meter. So this is gives you the dimensions of the compressor. Next is the enthalpy at discharge of the compressor, H2. So corresponding to this temperature and entropy, you can find out H2 from the graph straight away here, or we can do an interpolation. That will give you the enthalpy of 1703 kilojoule per kg. So now the power consumption is mass into H2 minus H1 divided by the adiabatic efficiency into mechanical efficiency. So that is the total power consumption which has to be provided to the compressor. So 181.7, which is in kg per hour, so divided by 3600 into your enthalpy difference. So H2 we have estimated, so 1703 minus the inlet enthalpy 1443.9 divided by the efficiencies. So adiabatic 0.85 and mechanical 0.95 will give you 16.21 kilowatt. So in terms of horsepower, you have to divide by 746, so that will give you horsepower, which is 21.73 horsepower. So now the theoretical COP is H1 minus H4 divided by H2 minus H1. H2 minus H1 is the actual thermodynamic work which is done on the compressor. So that will give you COP of 4.16. Because of this inefficiencies in the compressor, the adiabatic efficiency and mechanical efficiency, when you substitute Q by W, so Q naught, which we have already calculated, 54.43 here, first part, and work which we have calculated previously. So substituting that, we'll get 3.36. So this is basically because of the inefficiencies in the compressor. So that's why there's a drop in the actual COP, because you are consuming more work. So any doubt in this question? Okay then. So with that, I'll go to the next question. So an ammonia refrigerating machine has working temperature of 35 degrees Celsius in the condenser and minus 15 degrees Celsius in the evaporator. So just like the previous problem, so just an variation of that problem. So assume two cases, one A, dry compression, and B, wet compression. Calculate for each the following: 1. The theoretical piston displacement per ton refrigeration, the theoretical horsepower per ton refrigeration, and the coefficient of performance. So this is the problem. We are assuming two cases. One is dry compression and other is wet compression. So dry compression is like this: 1, 2, 3, 4, and wet compression is you are passing two phase into the compressor. So 1 dash, 2 dash, 3 and 4. So refrigerator circulation rate per ton of refrigeration is 211 divided by 1077.8 is H1 minus H4, which we found it in the previous problem. So H1 minus H4, so that gives you mass flow rate as 0.1956 kg per minute. So theoretical piston displacement per ton is again the actual mass volume flow rate into 60. So that gives you 5.975 meter cube per hour. So the theoretical horsepower is your work done divided by your horsepower, 736. So it will come out to be 1.15 horsepower per ton of refrigeration. Here this is not 90, this is 60, so there is a mistake here. So m dot by m dot into W is your work divided by, you are converting that into your hour. So this is in kg per minute, so you are dividing by 60 to convert into kg per second into your specific work across the compressor, divided by 736 to get your in terms of horsepower. So with that you will get horsepower. So COP is Q naught by W. So in this case it will come out to be 4.16, so which we saw in the previous case also. So it's same. So this is the same part of the question. So next is wet compression. So in this cycle, the cycle is shown in 1 dash, 2 dash, 3 and 4. So the dryness at suction can be calculated by interpolation for entropy. So in this case your exit of the compressor is the saturated vapor. So from there you follow the constant entropy line, and that entropy is equal to the S1 S1 dash is equal to S2 dash, and we can find out the entropy at saturated liquid and saturated vapor, and your S1 dash will be equal to X into saturated vapor entropy plus X into your SF minus SG, so SG minus SF. With that we can find out the dryness fraction here, so that will come out to be 0.88. So with that the corresponding enthalpy can be found out. So enthalpy is 1286.1 kilojoule per kg, and the specific volume here is 0.448 meter cube per kg. So with that the rest of the part is same. So Q naught and W, we find out the Q naught is H1 dash minus H4, which is 920 kilojoule per kg. Here it was 1077.8. So here it's lesser because it's the inlet is now inside the two phase. So W again is H2 dash minus H1 dash, which comes out to be 202.5 kilojoule per kg. So the refrigeration circulation rate for now this case is 0.229 kg per minute, because now the density is also more to the compressor, so there is more mass flow rate across the refrigerant loop. Next is the theoretical piston displacement, is again mass into your specific volume into 60 to convert into meter cube per hour. So 6.159 meter cube per hour, so that you are converting into horsepower the work, and similarly COP will come out to be 4.55. So the only difference here is previously dry compression, the inlet was at saturated vapor. In wet compression case, your outlet of the compressor is at saturated vapor. So that is the case to solve this. So rest of the part is all same. Any question in the previous problem? Okay then. So the next question is, a simple refrigerant R134A heat pump for space heating operates between temperature limits of 15 and 50 degrees Celsius. The heat required to be pumped is 100 megajoule per hour. Determine the dryness fraction of refrigerant entering the evaporator, the discharge temperature assuming the specific heat of vapor as 0.996 kilojoule per kg Kelvin, the theoretical piston displacement of the compressor, the theoretical horsepower of the compressor, the COP. So the specific volume of refrigerant R134A saturated vapor at 15 degrees Celsius is 0.04185 meter cube per kg. Other relevant properties also given. So whatever is required is given. So the inlet saturated vapor specific volume is given. So this is operating between 15 and 50 degrees Celsius. So that is given, and the specific heat is given, and we also know the saturation condition, enthalpy and entropy for both the temperature ranges. So we need to first find out the dryness fraction of refrigerant entering the evaporator. So H3 there is your saturated liquid enthalpy at 50 degrees Celsius. So that is 271.62. So this is equal to your H4, so inlet to the evaporator. So there it's a two phase. So we have to write it there. Your 15 degrees Celsius enthalpies, liquid and vapor. So you can find out dryness fraction. It will be H3 minus HF divided by H1 minus HF. HL minus HF. So X will come out to be 0.274. So that is the dryness fraction of the fluid when it's entering the evaporator. So now the discharge temperature is S1 is 1.72, which is the exit temperature, exit entropy of the compressor, because it's an isentropic process. So it is 1.72, and that is equal to we know the saturated entropy, vapor entropy at 50 degrees Celsius, which is 1.7072 at 50 degrees Celsius. So 1.7072 plus your entropy change because of changing from 50 to some temperature. So 1.7072 plus 1.246 is your Cp of the vapor into ln T2 is the final temperature divided by the initial 50 temperature 50. So 273 plus 50. So this is basically we are finding the entropy at state 2. So for that we don't know any other property. So with the table we are trying to find out the temperature. So we know the exit temperature, so that is equal to your saturated vapor entropy at 50 degrees Celsius plus entropy change because because your compressor temperature is somewhere higher than 50. So Cp ln T2 by T1. So T1 is your 50 degrees Celsius because that's the entropy we know. So with that we can estimate T2 as 327.15 Kelvin, which is 53 degrees Celsius. Next is enthalpy at discharge. So again H2 dash is your saturated vapor enthalpy at 50 degrees Celsius, 423.4 plus Cp is 1.246 into your we know the temperature at exit 53, so 53 minus 50 we come out with 427.2 kilojoule per kg. So with that we can find out the mass flow of refrigerant. So we want the heat is 1000 megajoule per hour. So 100 megajoules. So 100 megajoule is 100,000 divided by 3600 to convert it into per second. Divide by H2 minus H3, because this is in heat pump we have to take it across the condenser. So 427.2 minus 271.62 will give you 0.179 kg per second. And similarly theoretical precision displacement volume is mass into specific volume, which will give you 7.539 into 10 power minus 3 meter cube per second. And just similarly you have to find out work done and heating capacity. Work done is H2 minus H1, which is 3.6 kilowatt, and heating capacity is now, because heat pump you have to consider condenser, that is your desired output. So M into H2 minus H3, that is 27.9 kilowatt, and COP in this case will be the condenser specific heating capacity per unit refrigeration divided by the work done per unit of refrigerant mass. That will give you 7.75. So we have already found out the Q and W. So COP is Q by W, which will give you 7.75. See, both are same. So if you see in terms of quantity, only 3.6 kilowatt of work is consumed, but you can give 27.9 kilowatt as heat to whatever space we have to heat. So if you use a simple electric heater, that will give you only 3.6 kilowatt, but using this heat pump, instead of 3.6 it is giving 27.9, so it is giving 7.75 times more heat to the heating space. So this I think this is the final problem. So consider a basic ammonia refrigeration. Any question in the previous problem? Okay. So consider a basic ammonia refrigeration system using ammonia water solution as shown in figure. So pure ammonia enters the condenser at 2.5 megapascal and 60 degrees Celsius at a rate of 0.022 kg per second. The ammonia leaves the condenser as saturated liquid and is throttled to a pressure of 0.15 megapascal. So ammonia leaves the evaporator as saturated vapor. Heat is supplied to the generator by geothermal liquid water that enters at 135 degrees Celsius at a rate of 0.35 kg per second and leaves at 120 degrees Celsius. So determine the rate of cooling provided by the system and the COP of the system. Determine the second law efficiency of the system if the ambient temperature is 25 degrees Celsius and the temperature of the refrigerator space is 2 degrees Celsius. The enthalpies of ammonia at various states of the system are given as H3 is 1497.4 kilojoule per kg, H4 and Hc is also given 482.5 and 1430. Take the specific heat of water as 4.2 kilojoule per kg degree Celsius. So this is your system. So you have condenser, evaporator, generator and absorber. So this is a vapor absorption refrigerant system which we saw. So the rate of cooling provided by the system is across the evaporator. So m dot of refrigerator into H6 minus H5. The refrigerant mass flow rate is given as 0.022, and H5 and H6 is already given in the problem here. So H5 is the same as H4. So 1430 minus 482.5 gives you 20.9 kilowatt. So that is the cooling provided by the vapor absorption in the refrigeration system. The rate of input to the generator is the mass of the water coming. So here to the generator, so from the geothermal liquid water, which is 0.35 kg, is coming at 135 and going out at 120. So m dot Cp delta T, so 0.35 into 4.2 into your temperature, so 135 minus 120. So here we have to substitute in terms of degree Celsius, so kg degree Celsius. So 22.1 kilowatt. So then the COP becomes QL by QG. So that comes out to be 0.946. So this is desired by the input. So desired is your cooling load here in the evaporator, and the input is your generator. So QL by QG. So that COP is 0.946. So if you see, this is equivalent to running a heat engine and a refrigerator. So this, which we talked in the start. So that will come out to be 1 minus T naught by Ts into TL by T naught minus Ts. So next is if you substitute here, so the theoretical actual COP which you can get is, so substituting this temperature values, the T naught is 25 degrees Celsius plus 273, which is the ambient. So the condenser and absorber will be at the ambient temperature. So ideally it will be an ambient temperature. So 25 degrees Celsius, and Ts is your generator temperature. So the generator temperature is the mean temperature difference. So it is coming at 135 and it's going at 120. So that mean is 127.5. And similarly here the evaporator temperature is 2 degrees Celsius and the ambient 25. So substituting all the values, you'll get COP will come out to be 3.06. So if you see second law efficiency, the actual COP by the ideal COP, so it will come out to be 0.309 or 30.9%. So with this I finished all the problems prepared for today. If you have any doubts on today's week pertaining to vapor compression systems or refrigeration system, you can ask. Next week we'll look at psychrometric charts and how to solve those problems when air, it's not dry air but you have water mixed with that. So any questions you can ask. So if there is no other question, we'll end today's session. Thanks for joining. So we'll see next week on psychrometrics. Okay, thank you. So if there is no other question, we'll end the session. Do you have any question? Okay, since there is no question, I'll end the session. Thanks for joining.